Hey everyone, this video is continuation or rather part 2 of a previous video that I did just 2 days before of getting the sentiment classification using FinBERT on a long corpus of text. And the main problem that I dealt with there is that FinBERT or BERT in general has a token limitation length of maximum 512. That is, it can accept tokens or text whose tokens has a maximum length of 512. So what will we do when we have a text corpus, long text corpus, where the token length is much larger than 512? So this was a problem we dealt with in the previous video, and a solution technique was that I used a sliding window. That is, I chunked the whole text into 512 segments and then slided the whole window over the entire text. And for each window, I got a classification, that is sentiment classification, applying FinBERT, and then I took a mean or average over all the prediction for all the individual window, and that mean prediction or the mean classification is the final classification or sentiment classification for the whole corpus of text. So that's how we dealt with the problem of handling large token length text. And in this video, it will be a small change only, where instead of using various other normal Python splitting of the whole text, I will be using a method specific to PyTorch to split the whole text into different window and then get the mean prediction. So that's the only kind of change in this video over the previous one, that is part 1, and otherwise the overall approach to handling the problem remains the same. Let's start. Note, in the previous part 1 of this video, when I was using a pure Python way of splitting the text, I did not use this part, return tensor pt, because in that case, so that means that if I don't use this return tensor equal to pt, then these tokens will just be a normal Python list, and that will not be a PyTorch tensor. And that was a reason in the part 1 of this video I had to convert the list back into PyTorch again before the final steps. But now in this video, I'm going to use right from these steps this return tensor equal to pt. That means I am going to get back as my tokens a whole fully PyTorch tensor. So I do not have to go back and forth between Python list and PyTorch tensor in here, and that's the main benefit of handling the whole problem with PyTorch. So that's my tokens, and okay, and I'm just going to print my tokens and also print len of tokens. Let's run this notebook. And after running this cell, I get this output. Definitely this has been truncated. What mainly it is showing that these tokens is a dict with input IDs, token type IDs, and attention mask. And here this tensor, actually input IDs is a two-dimensional tensor. Actually it has been truncated, and attention mask is also a two-dimensional tensor which has been truncated here. So what I want to do right now is to apply the windowing technique over this tensor of input IDs and also attention mask. That is, I'm going to build one single window, or rather multiple windows, where each window is of a token length of 512, and then get as many windows as possible. Obviously the last window may be lesser than 512, and where I have to use padding to fill up the leftover places. So basically, it is the same approach I am taking here, what I did with the previous video. That is part one here. So only change is that in the previous video I used plain Python to make these windows, and here I'm going to use PyTorch split method to split this entire long tokens, so that I do not have to again transform my list into tensor down in the notebook, because in the previous video where I got Python list and then later I had to transform again to PyTorch tensor, those kind of back and forth calculation is not needed here, because here I am only working with PyTorch tensor. Now about the split method, let's quickly go over the documentation in PyTorch. So this is the method that I'm going to use, and it splits the tensor into chunks. Each chunk is a view of the original tensor. And what it does is that, for example, I have an original tensor A, which has 7 elements, and we can say it's a two-dimensional tensor. And then I apply torch.split on this original tensor with a number of split of 2, and I get a result where I get a split or chunks where each chunk has 2 elements. This has two elements, and the last one obviously has a last leftover because it has only 7 elements in the original tensor. Okay, so this is the one that I'm going to use. Before that, quickly check the length of the input IDs. And because this is a list of lists, so I'm going to use a 0 over here. Yeah. Okay, so we have 1653 as the total token length of this entire text, and obviously that's what the problem is. That is, FinBERT or BERT in general cannot accept this whole token as it is, because 512 is the limit, and that's the whole reason that I need to split it into window of 512. So yeah, next, input ID. And just like the previous video, I'm using 510 because I need to keep 2 places for the 2 spatial token called CLS and ACP at the beginning and at the end of each chunk. So those 2 I'm going to add later after this line is over. And just like this, I need to do it for attention mask as well. Okay, cool. Yeah, can I check the length here? Let's try. Attention mask chunks. One second. This has a different meaning. Let me clarify. So if I print these attention mask chunks, I got the length of attention mask as 4 because when I print the entire tensor, I got this tensor. And obviously it is not showing the entire thing because it's full output data in a text editor. Yeah, so when I open that entire tensor in a text editor, this is a long tensor I get. And what you see is that the original total text has been split now into 4 different parts. And this is the first window, then this is the second window, this is the third, and the last one is a leftover. So, and each the first 3 windows are should be each one should be 510 because that's what I mentioned here when I was splitting it. Split 510. And you can check that actually by just doing this length of attention mask chunk 0, and that should give you 510. Yep. All right, now Okay, that was just splitting it into 510, and now it's time to add my CLS and separator token. And we already discussed the CLS class ID is 101, and separator, that is the ACP class ID, is 102. And I am going to use torch.cat, which to concatenate these two to my to the beginning and end of each of these 510 tokens. But all these things I'm going to do with a single util function. So let's start writing my method where I will be doing all these mechanisms. Tokens. I need to take the input IDs. Just like before, we need to take the 0th index, and then on top of that, to that, I need to apply the split method. Split should be 510, what we saw here. But now here I'm going to use, actually, I could use 510, but I'm just going to use chunk size minus 2 to be explicit about what I'm doing here, that I'm keeping 2 for the 2 special tokens. Do the same for my attention mask. Oh, yeah, sorry. I need to change this here as well. Now I'm going to start a loop for the our previously we already have calculated what is this input ID chunks. So I'm going to run a loop for the length of these input ID chunks. For I add the it's time to add the special token of CLS and separator to these input ID. So torch.cat. Let's, the first one would be torch.tensor. That's for the CLS token. Then next one is just input ID chunks I. Last one is for the separated token, that's torch.tensor. (102). Okay, similar operation I need to do for the attention mask, but for the case of attention mask, it's not, instead of CLS and the separator token, I just need to add the class ID of 1. So attention chunks I. Yep. All right, now I still need to add the padding to our tensors to push them up to a length of 512, and this padding should only be required for the final chunk. So to do this, I am going to bring in an if-else statement that checks if the tensor length requires padding, and if so, then add the correct amount of padding. So let's see. So my boolean variable right now here will be not boolean actually. It's just a variable for controlling my if-else statement. So pad length should be chunk size. Ready chunks. I dot shape 0. Why I'm taking this? Because we have already seen for any particular element of input id chunks dot shape, that will give me the size. And the size here before this method is 512, but after here in this method by at this line it will be 512 because I have already added the CLS and SCP token. Now this pad length will be required only for the last tensor, but anyway I'm checking it for every turn in the loop, that is for every iteration in the loop with this I here. So for except for the last chunk, this pad length will be 0, but for the last chunk this pad length will be greater than 0, and that's why my if else statement will be pad length. Only then I need to add the pad, so that means input id, sorry, input id chunks I. Same technique, I'm just doing torch dot concatenation I torch dot tensor. I need to add a 0 for all these positions, so 0 multiplied by pad length. Yeah. And I need to do the same for the attention mask as well. Mask. Let's copy it. Why it's saying not defined? Let me say attention mask chunks. Anyway. Okay. And here. Yep. Finally, return ID chunks and attention mask chunks. Yep. Oops, sorry. Okay, now in my next sentence, I'm just get, yeah, and so up to this time, everything looks all right, and now I need to define a dict because in the finals, that's the final step, and this dict will just follow the style of FinBERT. Because we know FinBERT, we already saw that tokens has these key, this dict format, which has a key of input IDs and attention mask. So I'm just stacking all these individual tensor with torch.stack. Similarly, attention. Okay. Attention masks chunks. Yeah. So this is like the combined after stacking. This input ID and attention mask is the has all the tensor stacked together. And now defining dict called input date. Input ID should be in the long format, so I need to do input ids.long and attention mask should be in int format. Yeah, just want to print this and see everything is just working right. Yeah, looks all right here. And yeah, I just want to check another thing, the length of this. And here is the shape, and that's exactly the shape I wanted it because uh, and I can also check. Let me check input dict attention mask dot shp. Yeah. So now this shows that this is exactly the shape which will be acceptable by FinBERT because I have the max token length of 512, which is what FinBERT expects, and this is also called the sequence length. And the 4 here is just a batch size. Why? Because our entire all tokens have been divided or split or chunked into these 512 segments each. So yeah, so that's a shape I needed. So yeah, now I can just invoke my model to get my outputs. Outputs equal to model. We already defined a model. Input date. This model, these outputs are actually the actual logits value before softmax, and to get the probabilities I need to apply softmax. Puts 0 dim equal to -1. The spelling mistake. Let me correct it. Probabilities here. And then mean probabilities, because I also need to just I have already explained in the part 1 that after I get the probabilities, I need to get the mean, because that's the whole purpose, that I from these probabilities I can get individual chunks classification score, or the probabilities or classification label, but I need for the whole text, and for that I am going to get the mean probabilities, and from that mean probabilities I will apply argmax to get the classification for the entire text. That's the whole purpose of this problem. That is, even though I have much larger token size, but I divided into 512 token and then got the individual probabilities for the individual chunks. But at the end, I'm getting the mean to get my whole text classification score. Mean probabilities. PRLITIES. That would be probabilities dot mean across dim of 0. Let me just print this. It will, yeah, okay. Fantastic. So this is the mean probabilities for the 3 labels. FinBERT has 3 labels, 0, 1, 2, and that's actually for negative, positive, and neutral sentiment. Now I need to apply the argmax to get my the ultimate single classification for the entire text. So torch.argmax probabilities dot item, and that gives me 2, which is exactly what I got in part 1 as well when I was doing in Python. And this 2 means that it's a neutral sentiment for the entire text. And what was my text? this is the text that I have taken from this link right here. It's about some crypto's regulatory market report, etc. So yeah, that pretty much wraps up this video. So in summary again, that I just the problem that was solved in this video is to handle text which is much longer than 512 tokens, because 512 token is the limit of FinBERT or BERT, but we handle that problem by taking a longer text and split that text into different segment, and ultimately got the mean sentiment score for the entire text. All right, that pretty much wraps up this video. If you have liked this one, smash the like button and also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.